Ionic propulsion by Ivan. Ionic propulsion is a propulsion method used by a spacecraft which creates a cloud of plasma where the positively charged ions in said cloud are accelerated out the back by a negatively charged grid. The cloud of plasma is created by injecting a neutral gas and injecting electrons into the same chamber. What happens is the electrons bump into the gas molecules and cause the gas molecules to lose an electron, resulting in a cloud of electrons and positively charged ions. This is the plasma that was being referred to. To keep the negative electrons and positive ions separate and to prevent them from creating neutral molecules again, positively charged magnets are used to pull the free electrons away to keep the two apart. At the exit of the chamber are two magnetic grids spanning the entire length of the opening. The inner one is positively charged and the outer one is negatively charged. What then happens is the remaining free-flowing electrons inside of the chamber are attracted to the positively charged grid, but are prevented from leaving by the second negatively charged grid and the positive grid pulling back on them. The ions, on the other hand, are repelled from the positive grid, but the immense pressure inside of the chamber and the negative grid end up pushing them through anyway. When the ions get to the other side of the positively charged grid, the negatively charged grid accelerates them with help from the positive grid pushing on them to extremely high speeds, which generates thrust. When the ions have left the chamber and are out in space, to prevent them from coming back to the thruster because of the negatively charged grid, free-flowing electrons are injected into the stream of ions to neutralize them and bring them back to their original state. The first person who wrote and published a paper on the topic of ionic thrust was a Russian rocket scientist, Konstantin Tsiolkovsky, in 1911. The first actual working ion thruster was built in 1959 by Harold R. Kaufman at the NASA Glenn Research Center. It used mercury for its propellant, and in the 1960s, suborbital tests were conducted, and in 1964, it was sent into suborbital flight aboard the Space Electric Rocket Test 1. It successfully orbited for its planned 31-minute flight before falling back to Earth. Ionic thrusters have a 90% efficiency and can be run for years, but unfortunately they produce an extremely low amount of thrust, about equal to a piece of paper here on Earth. An ionic thruster would not even be able to hold up its own weight, but due to their ability to create a low amount of thrust over a long period, their application in the real world is not being used to get spacecraft into space, but instead be used once spacecraft already in space. In space, there's not much resistance to moving objects, which means that even though ionic thrusters do not generate a lot of thrust over time, they can accelerate objects to extremely high speeds. They also are used to rotate spacecraft and reposition them. The main type of propellant used is xenon, a heavy gas that was chosen due to its weight. A notable spacecraft that used ionic propulsion was NASA's Deep Space One rocket. It launched on the 24th of October in 1998, and its mission was to fly by asteroid 9969 Bradley. It was only partially successful because of the spacecraft was not as close as intended due to the fact that it had to keep readjusting its course. Starlink satellites also use ionic propulsion as they orbit Earth. Every year, ionic thrusters get better and better, and at some point in the future, they might be able to be used efficiently on aircraft. They have only been experimented with on aircraft, but at some point we might be able to see a large commercial aircraft using ionic propulsion. Ionic thrusters of this magnitude of strength might being used in space would allow us to be able to reach far off places in a significantly shorter time.